Okay, good morning, everyone. Thank you for coming. Paul. We have thousands of people in the audience, so I've got to be very good right now. Okay, so I do have a script in case I talk for too long. But my name is Simon Martin. I'm the sales manager for Domo Broadcast. Got 20 minutes to talk to you about what our technology is. So we have a portfolio which is IP mesh. And what I want to explain to you is, what is IP mesh? How does it work? What can it do in broadcasting? And how can it help in remote production and REMI? Okay, so our IP mesh system, it provides a bi-directional private IP network. Domo uses COFDM, like wireless cameras. So we use that modulation with time division multiple access. And our waveforms give COFDM range, the sort of range that you would get from a wireless camera system, but very stable latency and data throughput. Some of the functions that you can put onto this network, they sort of include like communications. So we've got a native talkback system on there, pretty sophisticated. And it also integrates with our Onyx REMI encoders. We'll talk about that a little bit later. But mesh can be used for third-party communication systems. So we could use Unity, GreenGo, Readle Communications, Clearcom, etc. That sort of stuff can be put over the top of us as well. We've got a demonstration on our booth over in the Central Hall. We're on C3020, and we've got a remote buggy. And on that remote buggy, we've also got a shot-over gimbal camera control, camera on there, and paint. So all those systems are put on the same frequency network. Camera control can be RS data, or it can be IP, so it can be native. You can use pan, tilt, and zoom control as well, so PTZ control of cameras. Telemetry, vehicle requirements are the parameters, athletes, biometrics, that sort of stuff can be put onto the network as well. GPS data, don't need any explanation for that. So some of our mesh radios have GPS receivers in them. And you can use it for return video communications to the talent in front of the screens. And auto cue as well. So there's a little video now, just to sort of explain what's what, and then I'll go through and do a bit of a recap for that.
IP mesh. What is it? Fundamentally, it is a single frequency, multi-node IP network. In a traditional wireless camera system, there is a transmitter and a receiver. In a mesh network, every radio is both a transmitter and a receiver, so they are called nodes. DTC employs a time division multiple access, or TDMA protocol. We use a token managed channel access system, whereby each node in the network is given a time slot to transmit. The token is passed from node to node depending on network parameters and data traffic. So if one node has more data to transmit, it will have a longer time slot. A particular node can be the endpoint for data, or it can be a repeater on the path for the ultimate destination. IP mesh constantly readjusts itself as nodes move, working out which are in range and finding the best route to send data. When one node can no longer operate, the rest of the nodes can still communicate with each other. How is this technology applied to broadcast? Working with mesh, it is possible not only to have video and audio wirelessly from a camera, but to have communications, camera control data, return vision, GPS data, athletes' biometrics, vehicle parameters, and even auto cue data on the same network. This can greatly simplify rigging of multiple different systems and all on a single frequency, rather than separate links. IP mesh is perfectly suited to providing coverage from mobile platforms, as in yacht racing, motorsport, cycle racing, and marathons. Mesh also enables coverage of large areas, such as golf courses, and events in difficult terrain where rigging of cables is not feasible, such as dense urban areas or in the mountains, And in these situations, aircraft and drones can greatly extend the area of coverage. Finally, it is also possible to connect separate mobile networks together using fixed infrastructure, such as dedicated fibre, the internet, cellular networks, and even satellite links. And this is called interlink mode, and it can greatly enhance remote production. Over the past few years, workflows have become ever more IP-based, and this trend is only set to continue. DTC's IP Mesh gives you a robust, long-range IP network to enable challenging productions now and into the future.
Okay, so that's a little bit of an overview of what it works. I'm going to go into like 3 or 4 slides now, just to sort of repeat, give you an explanation of the technology and how it works. So we use a COFDM waveform, same as wireless camera systems, but we've got time division multiple access into that as well. The way that our mesh system works is that every radio is every radio is a transmitter and a receiver. But we don't want everyone talking at the same time. So what we have is a token managed access system. So the token is passed from node to node, and a node can only transmit when it has that token. This is different to CSMA, which is some of the opposition sort of technology, a little bit like Wi-Fi. In the CSMA, the radios listen to see when they've got a free channel. And then when they think they've got a free channel, then they transmit their data. But what can happen in that situation is that 2 radios in the network might both think that there's a free channel and transmit at the same time. Wi-Fi is a brilliant technology, but we all know that when it's very, very busy, there's more and more people around, latency increases and the data throughput goes down. TDMA, our system, doesn't offer the very highest data throughputs. So on your data sheet, it doesn't look quite as good. But in the real world, you have better latency and your real-world data throughput stays higher when you've got many radios in the network. So when COFDM wireless systems came into being, the most popular question was, how far can it go? And it's the same question that we have today. The problem is with that is that we need to turn the question around to say, what is the range? Well, what you actually need, let's turn it around because we can help you. A few years ago, there was a guy, Felix Baumgartner, who jumped from space, highest parachute jump ever. He had one of our radios on. So how far do you need to go? He was like 100 miles up, right? So you can go as far as you need. With Mesh, we have a similar setup. People ask, what data rate do I get? And the honest answer is, we don't really know because it just depends. But we can work with you, and with that experience, we can make sure that you're getting the data throughput that you need. You can have higher power radios, you can have more radios in the network, so you can get coverage wherever you need it. So the next point is, I want to talk about the signal quality table. How does Mesh generate this? Every radio, every node in the network is a sensor. They're always listening to what's going on. So when the token is passed from radio to radio, it does so with a very short data transmission, but there's lots of information about the network in that token. All the radios receive this in the network, regardless of whether it's their turn to transmit next or not. And when the radio that has the token is ready to transmit, they work out which is the best connection, which is the best route. We'll go on to that in a little bit. When the node has the token, it populates the signal quality table with the information of which is the best route and which radios it can see. The token is passed around the network 300 times a second, very, very fast. So when you're talking about latency, there's very little latency added as far as our modulation goes. Very, very little latency is added. It's all just down to IP. Signal quality table is then used to set the modulation parameters for each link in the network to decide whether it's going to be a MIMO transmission, whether it's going to be a high order modulation at 64 QAM, or whether it's going to be much lower down at BPSK or QPSK. Now, how do we route data through the network? Well, we use Dijkstra's algorithm. And everyone's familiar with this. You've never heard the name, but everyone's familiar with this because this is the same as the way SatNav works. So if you're trying to get from one place to another, you don't always go the shortest route. You go the fastest route. So Dijkstra's algorithm is a way of working out the fastest route from home to school, for example, in this picture. You may go a longer way, but it will take you away from the slow traffic. There's a crash on the most direct route, it's going to reroute you, and that's the algorithm that is used. And we use exactly the same algorithm, so we're all familiar with that technology. We use it in a different way. So in the TDMA system, you want to use the lowest amount of time to get the data from your source to your destination, because this affects every other radio in the network and how much time they have left. So using this example, we can see to get from home to school, if we go via B, D, and F, it's actually a lower cost at only 9 than if you go from C and E. So we're going a longer route, but it's actually faster because we've got a higher order modulation, so we can get our data across those links faster. So to deliver IP data to the destination, Mesh will work out the best possible route, and this is per packet. So because we're updating the information 300 times a second, every packet of IP data is routed the best way. Now, there's one more thing on the technical side that I want to talk about before going into some of the applications, and this is interlink mode. So you can have nodes collected by different methods rather than just our own RF. We can connect them by Ethernet, we can connect them by 4G or 5G backbone, we can even connect them over Starlink and satellite links. So this can enable two different groups of radios to be in the same network. Now, this can be a remote thing, so you can be in different parts of the world, or you can have multiple networks at the same place, but working on different frequencies, but still in the same IP network. So if you need many, so the example would be, race cars, for example. You've got race cars in a track. You want 30 or 40 different radios in one network. You might want to have two different frequencies, but they can be on the same IP network. So, moving on, we've got a little bit of video now. I'll just explain what that's going to be. Now, this was it's a screen grab, so I do have to apologize for the quality of this. But this was a demo that we did at Lime Rock Race Track a little while ago now. I'm going to get the video playing. Right. So this is really helpful. So what we've got here, you can see video coming from 3 cars, and this is the mesh network. So this graphic here shows you where each car is on the track and the quality of the links between all the radios. Now, the data is not being sent over all those links all the time. It's been sent over the best links. So if you see the green links, obviously that's where it's going. There are links on there that you can see that are gray. Those are the ones in interlink. So they're put on a terrestrial network. They're connected by a Cat5. So the data coming off the car goes to the nearest and the best receive point. And once it's on that network, it stays on there. So all the RF, it doesn't need to retransmit on the RF. So this was a demonstration that we did for IMSA. It wasn't for broadcast quality video. This was for teams. So this was for the race car teams, so they could see what the drivers are doing, driver analysis. It wasn't just the video that we see there. They were taking vehicle parameters. They were looking at, when the race drivers were braking and accelerating. So it's for driver, building up awareness of what's going on to get the best, the best lap time that they could. Another application that we have, we did a little demo in Bogota, in Colombia, December last year. And what they wanted to do is to be able to have connectivity from motorcycles that were following cycle racing. So lots of cycle racing going on. So think of Tour de France, Giro d'Italia, things like that. But huge amounts of cycling goes on in Colombia. the way that they've been working previously is they were trying to use cell phones to have connectivity to people on the motorcycles. But when they're out in the countryside, they didn't have the connectivity that was well enough. So the system that we demonstrated had radios on an aeroplane, radios on 3 motorcycles. They connected back to our OB truck and then via Starlink to the MCR. So the guys in the MCR in the city of Bogota were able to speak to the riders on the motorbikes. They were about 60, 70 miles away from the MCR, but it was their own private network. And it worked brilliantly. We met yesterday with the guys. They're still trying to get budget for it, but it worked very well. And we're hoping that we're going to be able to demonstrate this equipment and this system to Tour de France and Giro d'Italia as well. So that was a very nice demonstration that we did, and it was a different sort of application. So here's an idea of what we did, or this is the network that we provided, as I explained. So we've got the cycles riding with 3 or 4 motorcycles connected to the helicopter and the plane, back to the OB truck that was in the mountains, and that was linked via Starlink. This was mesh for data and positioning and for communications. This wasn't for video. This wasn't for high quality video. It was a hybrid solution. So the high quality video was also using our equipment, but that was a single way COFDEM link from the bikes up to the airplane, multiplexed back, and then done over a satellite link as well. But what this really gave the really helpful thing for this was that the pilot in the plane doesn't always know where he needs to be. So with the cyclists, the guys in the peloton, there might be some interesting stuff going on at the back of the field rather than at the front. And so when he knows that he needs to be there, he can change his flight path. Having a GPS data, and we saw on the video before, we can overlay that onto real world maps and live maps, then he knows where he needs to be for the best of the action. And this is coordinated by the director back in the MCR, back in Bogota. Now, this is probably my favorite application that we've got for IP mesh. So SailGP. There's been a huge investment in the past few years in sailing. They really wanted to bring the sport more into a better viewer, more people watching. The amount of people that are watching has been growing. It's been doubling over the past 3 years. Every year it's been doubling. But what they needed to do for that was really up their game with the terms of the content. And so getting multiple camera shots off the boats, and controlling those cameras, getting GPS data for graphics was really, really inherent to being able to make a better content and a better program. The SailGP is much more complicated than America's Cup. In America's Cup, there's only 2 race boats on the course at each time. In SailGP, there's 8 at each time. Each boat has got 4 cameras on it. So imagine all those cameras being, you need to be able to get all those cameras back and switch them to get the best show. We've got a little video here, and I think there is audio over the top of it, but this shows you what mesh can actually do for it.
Hi, I'm Stevie Morrison, and this is SailGP Moment of the final day in San Francisco.
All the video
First
coming
up
back
was
is
race
over
to
data,
4
is
at
over
gate 2,
Domo.
and we can see a tight moment for both the USA and Spain looking for that left turn mark here. They're close coming in, but leading in is Jimmy Spittle on board the US boat. We can see he hits that yellow circle first. There's no overlap for Jordi Jamar. He isn't entitled to room, but he dives inside. And look at the consequences of that move. He ends up flying too high. He lands on board the American boat. We're on board here. We can see Jimmy Spittle and a vice at the back of the boat. My lord, are we glad to see there was no incident there. Rome Kirby diving out of his cockpit, and the drama didn't end there. Board the Spanish boat now and look to the bottom left-hand side of the screen, and we can see there the foils almost intertangled with each other, and it's the main foil of the Spanish boat ripping the back section, that blue section, off the back of the American boat there. Near capsize for the Spanish, and we see the angle on the back of the American boat. Rome Kirby jumping out of his cockpit, Jimmy Spithill, Paul Campbell-James almost pushing the Spanish boat off. Wow, I mean, it was lucky that no one was hurt in that, but as we see the overhead shots of the boat, we can see the back sacrificial part of the back of the boat ripped off, huge hole in the boat, but fortunately it wasn't too integral. The boat was able to be repaired and got ready for that final. But what a moment in that.
So all the data, all the video, all the data for the graphics, for the GPS, all the race control, all the communications was coming over a Domo IP mesh network. It's a little bit of a longer video, but honestly, a few years ago, I thought sailing was boring, but it really isn't. Just check out SailGP on YouTube. The highlights packages, really, really exciting stuff. So I've got a final example now of what's been doing, and this is a new race series, the E1 Electric Boat Racing Series. And the first race was in Jeddah just a few weeks ago. The next one is going to be in Venice in May. All these races are going to be produced remotely, with the MCR being back in London, but all the races being internationally produced. So this is how our IP mesh system can help with remote production. So Pristine Broadcast in the UK and Alcamel Systems in Spain, between them they use Domo COFDEM for the video links and for IP mesh, for comms, for race control, Teams broadcast, pan, tilt, and zoom control of the onboard cameras, GPS data. And then in addition to that, they're using our Onyx encoders for remote production. So they are the IP encoders and decoders that enable you to send very low latency data over the internet for remote production. This is the equipment that was used. So the RPM-TX, it can take 4 HD videos in and record all of these. You can transmit all 4 at the same time as a quad feed or just one. And you can ask for playback with anything over the air on a live return control link. The Sapphire RxD4 receivers stream straight out of the back onto the internet, and that was over the top of Tata. That was over the top of Tata network. Then on the mesh radios were the SDR 2x1 watt robust units. That's the picture in the middle. And finally, the Onyx IP encoders and decoders, which I mentioned for the remote production. I'm just going to go straight to the video because this is really cool stuff as well.
We go racing! It's absolutely sensational. A 101.98.
All out speed.
It's Eric Stark who takes victory for Team Miami.
Over Duncan, having an absolute storm on the...
But look at Team Brady, who are now out in front. They're victorious here at Jeddah.
Look at this battle going on now.
Rafa will celebrate its victory for Tom Schaap.
Brilliant race from the Frenchman. What is going on?
Incredible. Sam Coleman is laying down the hammer.
So sorry I had to cut that short. I've been wittering on for too long. I've been told that I have to stop now. But all the data coming over the network, all the management, all the video was all coming through Domo Systems technology, where we've got a display over in the central hall, C3020. We'd like to speak to you. Anyone who's interested, please come and speak to us after this. Thank you very much.